All right, first, thanks to the organizers for allowing us to have our talks and allowing them to have in sequence right after each other. And thanks to Mauro for proving all the most difficult results. Now we're going to go to differential operators, and it's going to turn out that getting nice results is a bit easier. So to recap, what we constructed is an infinite family of endofunctors on left A modules for some unital associative algebra, given an exterior algebra, which is also called differential calculus by some other people at this conference. And these are equipped with natural transformations, prolongations, and projections. And additionally, we have the endofunctor of quantum symmetric forms. And now, the prolongation map is enough that you can make a reasonable definition of differential operators. So in particular, a linear differential operator is going to be any map between modules which factors through the prolongation map. So you have this triangle diagram. You can make similar things in classical geometry. That's where it comes from. And now, the important part is that this Jn is not a left module map. However, the lift delta tilde is going to be a left module map. So that corresponds to vector bundle maps through the Searles-1 theorem, if you want to think about that. If we had a good notion of more general bundle maps than vector bundle maps, then we could make nonlinear differential operators as well, but we don't, so we can't. So anyway, any operator delta between two modules that factors like this is going to be called a linear differential operator of order at most n. But it could also be a differential operator of lower order. So if n is minimal, we say that it's a differential operator of order n. So here are some examples of differential operators in this sense, or linear differential operators in this sense. First of all, let's suppose that our calculus, or the first degree term of the exterior algebra, is parallelizable in the sense that it's free and finitely generated by some theta 1 to theta n. Then you can define partial derivative operators. For example, you can do this on a coordinate chart on a smooth manifold. And it's just defined in terms of the differential by this formula. And secondly, we can define connections algebraically like this. It's just some map that goes from some bundle to the value of that bundle through the one-form functor. And it satisfies this Leibniz rule. Mauro didn't mention it, but actually splittings of the one-jet exact sequence for the bundle E are equivalent to connections in this sense. So that's kind of nice and geometric. And finally, the operator that we constructed to produce the holonomic jets, which is called EV, that's the D with the weird dash, is a natural differential operator of order 1 from the jets to this strange space. And you could also consider this in classical geometry, where it has actually been found, and I will talk about it later. I mean, it's a natural differential operator, so you expect that it's known. But it wasn't really used for anything there. So for us, it's fundamental. So it's kind of different direction. Now, first, some simple propositions. If you have a differential operator of order at most n, and m is greater than n, then this differential operator is also a differential operator of order at most m. So the proof is very easy. The projection map is a vector bundle map, so you just compose them with the lift that you already had, and this gives a new lift to the higher order jet bundle. So that works out nicely, and in particular you can get, for example, zero order differential operators lifted to any jet order. And it's a bit more complicated to show that the composition of two differential operators of order at most n and m will be a differential operator of order at most n plus m. That follows from this diagram. So the important part is that this map here is left linear. So in particular, it's a morphism of left A modules. And therefore, we can apply the jet functor to it, and you get something reasonable here. And then you just compose everything, and you see that this composition actually admits a lift to the jet bundle order m plus n. So compositions of differential operators are differential operators, and that means that we can make a category which will have the same objects as the category of left A modules, but instead of vector bundle morphisms, we consider the morphisms to be differential operators, linear differential operators of any order. And in particular, this means that the differential operators from a fixed object to itself will form an algebra. And in the particular case where the module is the algebra A itself, we're going to call this just D. So D will be the algebra of differential operator from A to A. An important fact about D is that the algebra A op, so that's A with the multiplication reversed, embeds into D as zero-order differential operators, always, because it's left linear. So that just comes from the right action of A on itself. But if A is strictly non-commutative, then left multiplication maps are not left linear, and so left multiplication maps are not zero-order differential operators. And for a given calculus, it is not necessary that they are differential operators of any order. However, I will show soon when they are. So we have a construction which we call terminal calculi, and we invented this because of this this phenomenon, basically. So we would like for some algebra elements to find for which calculi the left multiplication by these elements are differential operators of order at most 1. Of course, if your algebra element is central, then it coincides with the right action, and so that would be for any calculus. But in general, it's not so. So it turns out that there's a minimal first-order calculus. The first-order calculus is just a degree 1 term of the exterior algebra, which has this property. And they can be defined by directly constructing the kernel ND. And if you have a singleton set, we're going to call this NF. So that's the differential relations for F. So in particular, you have this, this map which takes M tensor N to MFN inside A. And now M tensor M, actually it should be a sum because it should be in the kernel of the multiplication map, but I forgot to write the sum symbol here. And so you can construct for a singleton this so-called terminal calculus as A applied to the commutator in the classical sense of the element F and A, which is just some submodule of A left submodule of a bimodule. And now the differential is just the commutator between F and A. And so this coincides with the notion of inner calculus, which is quite popular in noncommutative geometry. However, we generalize this by taking sets of elements. Let's say S is some subset of A. And then the terminal calculus for S is just going to be the calculus for which the differential relations is the intersection of the differential relation for all the NF. And so you can see it in symbol here. Perhaps it's easier to understand. And so this omega 1s, which is just a quotient of the universal by this, is going to be the terminal calculus for S. The structure of the category of differential or first-order differential calculi is quite simple. Because of the surjectivity condition, you have that all maps are bimodule maps, and when they exist, they are surjective and also unique. So it's very rigid. And about the differential operators, if you have two calculi and there is a morphism between them, then the differential operators for the codomain calculus are also going to be differential operators for the source calculus. And so this terminal calculus for S is going to end up being the terminal object in a new category of first-order differential calculi, which consists of all of those for which all elements of S are differential operators of order at most 1. And that gives us a nice tool to produce some examples. So let's move on to the example portion. So we are just going to work with the quaternions because they are the nicest noncommutative algebra, in my opinion. It's a bit of a toy example because it's finite dimensional and some special things happen in finite dimensions, but still you'll see that it will become quite geometric. So hopefully you all know what they are. And because it's a division algebra, the category of left and right modules are really well behaved. They are called quaternionic vector spaces. And they are characterized by quaternionic dimension up to isomorphism. They're always free, so in particular, most of the homological conditions that we wanted from the previous talk are going to be automatically satisfied. On the other hand, the category of quaternionic bimodules are potentially poorly behaved. They can have non-trivial relations. So let's construct a terminal calculus for this. Basically what we want is the terminal calculus for I and j. So we want left multiplication by I and j to be first order differential operator. They're not zero order differential operator because it's non-commutative. So the universal has this nice form: I squared plus 1 squared, j squared plus 1 squared, k squared plus 1 squared. And when I write angle brackets, I mean generated as a module. You can generate from the left or the right, it does not matter. So we compute ni and nj, and we note that they have a non-trivial intersection. Take that intersection, which will be the one at the bottom here. And this is actually quite nice and computable because now you can just make expressions, and every time you see k tensor k, you replace it with this 1, 1 plus ii plus jj. And so we can compute the structure of this terminal calculus, and the non-trivial structure equation is given by dk, which is a linear combination of di and dj, linear combination over the quaternions. This is free as a left module, so it's parallelizable. It's spanned by di and dj. But it has a non-trivial bimodule structure, which you can see below, as I warned, is possible for quaternions. So now we can compute the differential operators, and the first thing that you want is the zero-order operators and the partial derivatives. And I write them in this vector notation. So it just means that di takes 1 to 0, it takes I to 1, it takes j to 0, and it takes k to minus j. So now you know how to read it. And then the full algebra of differential operators is generated by the zero-order operators, which are the right multiplications, and di and dj. And in this case, interestingly, you'll see a specifically non-commutative phenomenon. The partial derivatives do not commute. Because of the structure of the quaternions, it actually anti-commutes. And also there is some bimodule structure where, because the algebra of differential operators is an algebra over A op, which is given by the right multiplication maps. Now here, actually, all quaternions will be finite order differential operators. I and j, by construction, are, yes?
Yeah, so quaternions can be made as graded.
Sorry?
The algebra of quaternions can be viewed as a graded.
Yes, it's actually super graded.
Yeah, so it's what you just said is related to that.
Yes, it's a non-supercommutative supergeometry. That's the secret. Yeah, so anyway, not only h op can be embedded, but h can be embedded by the left multiplication maps. So li and lj are first order operators, and by the composition theorem, Lk is a second-order operator. You can verify that k is not a first-order operator as well. So it's actually of order 2. Now we can do some geometry with this. And in particular, the quantum symmetric forms are antisymmetric, related to the super property that he just mentioned. So it will be di dj minus dj di. And higher order quantum symmetric forms just vanish. So we have jet dimension stabilizing. The one jet has quaternionic dimension 3. The two jet has quaternionic dimension 4. And they are obviously isomorphic to the free modules as quaternionic vector spaces. It's a non-trivial statement that the second-order quantum symmetric forms are isomorphic to H as a bimodule. Like I said, that's not automatic. But it does happen, and this gives you a unique up-to-scale example of a so-called quantum metric. And so we wanted to do some geometry for this quantum metric, so we computed its Laplace operator, which you can see at the bottom of the slide, the Laplace-Beltrami operator. It's just 2 dj di. Well, depending on the scale you choose, of course, but we just chose the generator that you see up there. Okay, next example is going to show that we are actually generalizing classical geometry. We're going to be considering smooth manifolds. And we're going to take the exterior differential forms and consider it as a differential calculus. And this is basically the motivating example for everything. So this should work, right? So in particular, we need to show an isomorphism between jets of sections in the classical sense and our construction. And this comes from the diagram in the middle here. And basically everything comes automatically from the constructions that Mauro presented in the first part of the talk. The only really non-trivial thing is this map in the middle, which is given like this. And so we get an isomorphism by this formula. And you can verify that if this is a prolongation, then it goes to the classical prolongation, or the classical jet of the section through this isomorphism. And so you have immediately that the modules are isomorphic. The isomorphism intertwines the prolongation maps. And so they give the same differential operators. So for the point of view of geometry, it's absolutely the same. So from now on, we will just consider them to be the same. Now, for higher order jets, we need some structure theory. So in particular, there is this nice results from Goldschmidt, Quillen, and Spencer, who also worked in jets using mostly homological algebra from the 60s. And there is actually a differential operator in one of Goldschmidt's paper, which he calls ρ, that characterizes the J+1 jets inside the J1 of the N jets. And he proved that this operator is unique. That's very helpful for us because this uniqueness result makes it easy to identify Goldschmidt's operator ρ from the 60s with our operator ev tilde. And thus their kernels coincide, and so we immediately get that the two jets coincide. It's not that easy to use this result for the higher jets, but we have a different method for that. So in particular, our two jets are isomorphic to the jets of sections of order 2 for vector bundles. And again, the isomorphism takes prolongations to prolongations, so you get the same differential operators, and geometrically everything is equivalent. Okay, so some more structure theory. This result is actually from Quillen's PhD thesis, but that's a bit difficult to find. And it was also referenced by Donald Spencer in 1969. And it says that as submodules of non-holonomic jets, you have that n plus m jets is this intersection for all n and m positive. And this is what we are going to use to prove the equivalence of the classical n jets and our n jets. So finally, we arrive to the theorem which we call classical correspondence. If all the data is classical, so you have the algebra is C infinity M, the exterior calculus is just the RAM exterior calculus, and you are working with some vector bundle, or rather the module is the space of smooth sections of a vector bundle. Then the modules of sections of n-jets and our constructions are isomorphic, and again, the prolongation maps are compatible. So they're intertwined, differential operators are the same, geometrically everything is the same. So how to do this? Well, it seems we didn't have time to talk about alternative definitions of the jet functors in the first part. But there is a theorem there. If the one forms are regular enough, then you can get a similar intersection theorem to Quillen. And in this case, the one forms are actually a vector bundle, so they are maximally nice. Everything we could hope for is satisfied. And so we can write this intersection definition of the higher jets. And you combine this with the base cases for n equal to 1 and n equal to 2, which we proved separately. And then we can inductively prove this for all n greater than or equal to 3. And also you should verify that the prolongation maps coincide, but that's a bit separate. Okay, so that's all I wanted to say. I hope that the differential operators convince you that this notion of jet is actually not that bad. Thanks.